Okay, and now for the final talk of POPL, Stelios will bring us towards a higher order mathematical operation.
Nice one. So I'm Stelios. I'm happy you stuck here for me until the end. I hope it's good. And I'm also joined here by my good friend, Henning Urbat. So I'm going to talk to you about a categorical perspective on operational semantics. And I'll start with something strikingly non-categorical, a rule format. So the GSOS rule format is a popular rule format for process calculi. And it consists of basically a bunch of arrow expressions. You have a conclusion arrow here and some premises. Now, the source of the conclusion is an operator, and it's populated by a bunch of variables, just general variables. And then the premises on the left side, the source is one of those variables, and they represent sort of how these terms transition, right? And this label here, importantly, it's distinct from the variables. It's a selected set. Let's see a very elementary example. So you have this composition operator here, P and Q, P composed with Q. This says that if P transitions to P prime emitting A, then P composed with Q transitions to P prime composed with Q with an output of A. Now, the key observation here is that we make no assumptions on the shape of the variables here, of P prime, of Q. This can be anything. They are shapeless. They are generic. And this is really what Turi and Plotkin observed, and they made this mathematical operational semantics framework. They realized that from a categorical perspective, this kind of genericity of those variables amounted to naturality. So they said, you know what, in category theory, we can model the syntax of a language using an endofunctor. And you can model the behavior of a language using an endofunctor. And they said, well, if you have the sigma and the b here modeling the syntax and the behavior, then operational rules amount to natural transformations of this kind of type here. Now, a natural transformation is a parametrically polymorphic family of functions, like indexed on X here. And this might look a bit cryptic here, but I will try to explain it to the best of my ability. So let's see. Turi and Plotkin, one of their fundamental results was that given some signature or endofunctor, whatever you want to call it, and a finite set of actions L, they said that GSOS specifications, so the concrete languages, they are in a bijective correspondence with GSOS laws of sigma over this thing here, over this kind of behavior, which represents non-deterministic transition systems. So they said that to give a rule like this is equivalent with giving a family of functions like this. Roughly, the domain of this family of functions here is matched with the source of the conclusion and the premises, while the codomain is matched with the target of the conclusion. And I want you to understand this. I think it's didactic. I think it's worth spending a little bit of time on this, because I think it's pretty intuitive in the end. So what is on the domain? Well, you choose some operation, say F. In this case, we chose this composition, this binary operation here. And they say this is populated in this family of functions with pairs of things. What things? On the left side, we have just a generic term, right? So these are your generic terms. These are your x's here, all of these things. On the left side of premises. Now, if we focus on this here, on this variable here, this x represents the right side, the targets of those premises. If we focus now on the codomain, on the destination, we see here that this x, you have to populate this with either this or this, with green or red variables, so blue. In this case, we picked P prime and Q. So what this captures, what this thing captures here, what they say, what Turi and Plotkin say, is that operational semantics are just permutations, funny permutations. I don't know what I did here, sorry. So this bijective correspondence here this fascinated me, because for the first time, since I started working on operational semantics, GSOS laws gave a precise and concise mathematical representation of what GSOS specifications are, unambiguous. They're natural transformations. Now, this is all nice, and this is very parametric. For instance, you can talk about GSOS rules, you can talk about any other kind of rules you want. You can choose your category, you can choose your behavior, you can choose your syntax. It's a very general kind of framework. And it comes with other nice things. For once, each of those GSOS laws, they induce for free an operational model. Now, this thing here is a coalgebra, but you can kind of consider it a transition system. So by induction, you get for free a transition system on mu sigma here, which is just your object, your set of programs, which is inductively defined. Also, what we get is a denotational model, a sigma algebra, which you can imagine that it is a compositional kind of definition on co-inductively defined behaviors. And the good thing is, the key result of all this is compositionality. Your semantics are compositional, the operational model agrees with the denotational model, bisimilarity is a congruence. So if you have pairs of bisimilar terms, pi bisimilar to qi, then f of p1 dot dot p of n is bisimilar to f of q1 dot dot qn. And that's a very nice thing, all good. A very fundamental, nice property to have. Now, the scope of this is strictly first order. You can do CCS, you can do pi calculus, you can do, all sorts of process calculi. You cannot do the lambda calculus. You cannot do the SKI calculus. And no matter how successful this framework was over the years, because they did cover variable binding, they did do other nice stuff about effects or more languages, more formats, even some elementary work on compilers. The big problem was higher order languages, the big sticking point. In fact, it's something that Turi and Plotkin had laid their eyes on from the very first moment. And this is a quote from their paper. The major challenge ahead, from 1997. The major challenge ahead is the operational semantics of languages with binding, such as pi calculus and the lambda calculus. So higher order, there it is, the biggest prize, the most important higher order language. Now, fast forward 25 years later, and Hirstovich and Lafont say this approach, so the framework of Turi and Plotkin, has been deeply investigated. However, as of today, attempts to apply to higher order languages have failed. So apparently, people have been trying. So let's understand this problem with higher order languages better by introducing a very elementary combinator calculus. So here we have a bunch of funny arrows again. We have a combinator D, a singular combinator. We have application, and we have this feature that labels now can be terms. So you can see here, for instance, that T, you can use it to form complex expressions. And over here, this rule, actually, let's take its rule separately. If you apply T to D, then it's going to produce TT. If P better reduces to P prime, then PQ better reduces to P prime Q. That's like the lambda calculus. And now another classical rule of better reduction. If by applying Q to P produces P prime, then PQ better reduces to P prime. That's the standard lambda calculus application rule, all right? So let's see, is this GSOS? We're gonna compare the two, let's say there's a format here, this is supported by a format. So the first rule, is this GSOS? Yes, actually this is GSOS. This is perfectly fine. This invisible label, you can consider it as a select label from a certain set of labels. That's fine, it's perfectly fine, it can handle it. How about this one though? This one is not GSOS. And you can see the problem. This label here, Q, it's a term. We have probed term P, which behaves like a combinator, and produced P prime. This is a big difference compared to GSOS, which is like a distinct set, right? So this isn't supported by GSOS or anything like GSOS, like abstract GSOS, mathematical operational semantics. We're screwed. How about this one? Again, no, because as you see, the label here is a term. We use it sort of create a complex term. The fundamental, primordial problem with these behaviors, with higher order languages, is that combinators or lambda abstractions, they behave like functions from terms to terms. So if we were trying to do this generically, we would say that the behavior of a term is x to the power of x. But the problem is, and this is a primordial problem in category theory, that this assignment, assigning x to the power of x, is not functorial. We're not talking about an endofunctor. But instead, the best way to describe this in a categorical manner is by saying that we're assigning two things, two sets, say, x comma y, to y to the power of x. And this is bifunctorial. It's contravariant in x and covariant in y. So our idea was that instead of considering endofunctors and natural transformation is something that right now feels obvious to me. Consider bifunctors and dinatural transformations. In fact, I think people have thought of it, but there is some artistry on the semantics. That's where you had to prove how to actually pull it off. Anyway, that's what we thought of. So this should remind you of a previous slide. We defined a higher order GSOS law to be this kind of natural transformation here. We're once again modeling syntaxes as an endofunctor, but now we're modeling higher order behaviors as a bifunctor. And in this case, we have an indexed family of functions, which is dinatural in x and natural in y. And I want to stress that dinaturality here is the kind of suitable notion of parametric polymorphism for bifactorial functors. Whatever, I think I said this correctly. So let's try to again see why this makes sense as a kind of framework by specifying a rule format for combinatory logic. So this one here is a very simple format that says your premises can consist of beta reductions here or label transitions, where your labels, as you see, have to be taken from the subterms that are populating the source. So you're the target of the rule, if I may. And if we forget about sugaring and stuff, this kind of combinatory logic here, all these rules, are they fit this framework. So this type of rule here matches the second rule. We don't have any premises, but that's okay. This rule here matches the first rule, although we don't have any labeled kind of premises. And this rule of beta reduction matches again this rule here, although we do have, this time, we only have labeled premises. So what did we prove? One of the things, one of the early propositions in the paper, is that for every signature that represents, every signature we associate endofunctor sigma, HO specifications are in a bijective correspondence with higher order GSOS laws of sigma over this kind of behavior. And you can understand this kind of behavior as saying that your terms, they can either beta reduce in one step, or they behave like combinators. Let's try to do what we did earlier and see why this works. So what do we have on the codomain? On the codomain, we have a choice of an operator. This time is application. And it's populated with a pair of two things. And on the left side, we just have a variable, right? So there it is. There it is, x here, p, q, and p, over here on the premise. Now, if we look inside on the right side of this pair, we have y and y to the power of x. And this is the right side again of the premises. Now, this little x thing here, this actually matches with the q, right? As you see, you can apply this x over here to get a y. That's what happened here. And now, on the right side, we can pick either an x or a y, right? And make a complex term out of it. We picked something from the right side. We picked a y, the p prime in this case. So that's how this correspondence works. So we have now this nice framework. We have, again, a kind of correspondence between higher order rules and dinatural transformations. In the case of the combinator calculi, we pick the way we instantiate our parametric framework is we do things in the category of sets. Everything lives in the category of sets. Our end effector is like classical stuff, combinator, application, whatever other combinators you want. And your behavior is of this sort. Beta reduction or it is a combinator. Your term behaves as a combinator. Now, the big prize is the lambda calculus, and things were more complicated in this case. So for the call by name lambda calculus, you have to pick as your base category to be the category of set to the power of f, where f here is the category of finite cardinals. And this is from, we took this from work of by Fiore, Plotkin, and Turi, the beginning of the century. And this is pretty standard. That's how they model, that's the end of functor that models the syntax of the lambda calculus in their setting. As for the behavior, and this I think was the trickiest part, you have to understand that a lambda term, or at least in our realization, its behavior has two components. The first component here, I don't need to explain what it is exactly, but it represents a substitution structure, the substitution behavior of a lambda term, as in each lambda term exposes the way to substitute other terms inside of it. While its other component of its behavior, it's more standard. A term can either, in one step, better reduce, behave like a combinator if it's a lambda abstraction. It doesn't reduce anymore if it's a lambda abstraction, or it's stuck. It might as well be stuck. So in our framework, what do you get? Let's repeat the process from the parent framework of Turi and Plotkin. You do get inductively this operational model. You do get a transition system inductively on the set of or object of programs. The big problem is you do not get a denotational model. For various reasons, these are technical, I will spare the details. However, what we achieved was a compositionality result, that co-algebraic bisimilarity is still a congruence. The case is much more complex than the first order case, and I feel quite merciful today, so I will not show you any details about it. But I think it's worth pointing out what co-algebraic bisimilarity is for the lambda calculus. So co-algebraic bisimilarity on the lambda calculus amounts to strong applicative bisimilarity, a strong variation of Abramsky's applicative bisimilarity. Let's spell it out. So it is the greatest relation tilde on closed terms, such that for T1 bisimilar to T2, if T1 better reduces to T1 prime, then T2 better reduces to T2 prime, and T1 prime is bisimilar to T2 prime. Now, if T1 is a lambda abstraction, so say it's of the type of the form lambda x dot T1 prime, then T2 has to be of this form also, lambda x dot T2 prime, and for each closed lambda term E, substituting E on T1 prime is bisimilar to substituting E to T2 prime. So that's Brush two symmetric conditions. This is bisimilarity. So this should remind you of Abramsky applicative bisimilarity. It's like it's more fundamental variation, I would say. So that's what we did. For future work, we actually completed this. We did implement House method for weak or standard applicative bisimilarity. We're also doing good progress towards achieving proper call by value semantics. We then will look to very importantly start to support typed languages, and then why not implement other operational methods such as logical relations. That's a big target for us. And then, yeah, we can look at environmental bisimilarity, try to support this. I don't know how it works. Compilers, that's a nice one. And also mechanize it because, you know, we have a nice theoretical framework. It would be nice to be usable for PL people. That's the dream. And that's all from me.
Great, thanks. We have several questions. Ohad over here.
Thanks for a very nice exposition and clear talk. So in the Plotkin-Turi motivating characterization, you had a power set on the premises, right?
Yeah.
So you can have it non-deterministic.
Yeah, this is deterministic, by the way. Ours,
Exactly, yes.
This format, yeah, sorry, I didn't mention it, forgot. Yeah, it's a simple format. We decided to go deterministic. We also have a non-deterministic variation.
Thanks.
Yes. Okay.
Hi, thank you so much for the wonderful talk. So in the Plotkin-Turi paper from the 90s,
Okay.
there's this correspondence between the abstract GSOS laws and distributive laws of monads over comonads.
Yeah, it's.
Do you have something similar to that?
Yeah, we do. Didn't I?
I just might have missed it, sorry.
Yeah, there it is. We have something similar for combinatory logic, right? Yeah. So for set stuff, this is deterministic. We could have done things non-deterministically. Sadly, we don't have yet an idea to do the lambda calculus, like have a format which subsume the lambda calculus. But that would be very interesting to do.
Okay, thank you so much.
Hello, Jeffrey, Roblox. Okay, I'm glad you're on that slide because that is actually a slightly different presentation of the operational semantics for lambda calculus as expecting this style, in that it's got substitution as a meta property rather than as something that's actually got a transition system designed for it. So I'm always expecting the style where there's an explicit transition for substitute through with X. And it would actually be part of the operational semantics rather than here it's part of meta theory. So I was wondering if substitution transitions is something that your theory would be able to cope with.
I think you got it backwards. I think in this case we're explicitly defining the substitution structure. If this was missing, then that I would believe would mean that it's part of the meta theory. We do assume, yes, that each term has a substitution behavior, sure, but the way that the rules are presented, like this is only the component on this side, right? If you want to be precise as to how to define this GSOS law, this higher-order GSOS law, you have to explicitly say how for application, how substitution distributes over application, for instance.
I think let's take it offline.
Okay.
See, when you go to the typed version rather than the untyped version, does F stay on that slide?
Oh
Stay on
shit!
it.
Sorry.
Does F change to something like contexts and renamings between contexts? It's as simple as that, is it?
It should, yeah. Well, I would think, I don't know, but we hope. We hope it's that smooth. But yeah, instead of F, you're gonna have a category of typed contexts.
Yeah.
That will
renaming things between.
Yeah. But we hope it's that smooth, right?
Okay, wait, I do want a question. So for call by value, is the problem that you need to, similar to type, that you need to add a value expression distinction?
On a fundamental level.
Okay, so it wouldn't apply, when you say you want to do call by value, you mean it would need an extension?
So the problem, I can do call by value semantics. Operation semantics we can do. It's actually in the paper. The equivalence is wrong because the call by value by applicative bisimilarity, you don't want to quantify over all closed terms, but on values. And you don't get that for free, and there's no chance to get it, easy chance. But if you move to sorted sets, that's how we did it, you actually get it, yeah.
Great. Okay, thank you, Stelios, and thank you, everyone. POPL is over.